Hello friends, this video on solutions part 19 is brought to you by examfear.com. No more fear from exam. Let's redefine the Raoults law, right, based on the discussion we had. So as per Raoults law, for any solution, the partial pressure partial vapor pressure of each volatile component in the solution is directly proportional to mole fraction of that component. So that is my Raoults law. Please understand this. We're talking about solution. We're talking about the partial vapor pressure of each volatile component, and that is directly proportional to mole fraction of that component. Right? Example, this is my solvent, let's assume, and this is my non-volatile solute, and this is my volatile solute. This is a solution with non-volatile solute, and this is a solution with volatile solute. Correct? So if you see the mole fraction is 0, this is my vapor pressure of pure solvent is here. If the mole fraction is 1, that means I have pure solvent. You decrease the mole fraction, that means you add impurity, the pressure will decrease. Correct? This graph shows that this is the case of my pure solvent. This is my case here. You keep increasing impurity, the vapor pressure will decrease. Correct? So in this case of non-volatile, only solvent molecules are present. You see the red ones are not there, and the solvent molecules only contribute to the vapor phase. So in this case, if I want to write the total pressure in this P1 will be nothing but P1 naught into X1, and that will be my total pressure. In this case, I have to say P1 is equal to P1 naught into X1, P2 is equal to P2 naught into X2, and total pressure will be P1 plus P2. Correct? Because this is non-volatile solid, this is volatile solid. See, actually for a non-volatile solute, this P2 naught is 0 actually. Even if you say P2 is equal to P2 naught into X2, this will be 0. So it will come out to be 0. Because in the pure stage, that will not be volatile. Now let's talk about the ideal and non-ideal solution. Please do not get confused with ideal or non-ideal gas. I'm not talking about non-ideal or ideal gas. I'm talking about ideal and non-ideal solution. This is the ideal kit. This is a non-ideal kit. The definition is very simple. Solution that obeys Raoults law over entire range of concentration are ideal solution, and vice versa. Let me write this definition for you. Solution that obey Raoults law over entire range of concentration are called ideal solution, and vice versa is non-ideal solution. See, when they say entire range of concentration, is a solution may obey Raoults law when it is dilute, but may not obey Raoults law when it is concentrated. Right? So if a solution obeys Raoults law with the entire range of concentration, whether it is dilute, concentrated, medium, that means it is a ideal solution. And the reason why we are studying ideal solution is not because they are robbing Raoults law, big deal. The reason we are studying ideal solution is because there is some properties of ideal solution. Right? What is the property? The enthalpy of mixing pure component to form solution is zero. Enthalpy of mixing to form solution zero, because there is no energy required, or there is no energy liberated to mix solutes and solvent to form solution. That is the one property. Second is delta volume of mixing is zero. There is no volume gain or no volume loss when you form a solution. So for example, volume of solution will always be equal to volume of solute plus volume of solvent. There is no volume loss or there is no volume gain. Correct? The first one says enthalpy of mixing is zero, that is no heat is absorbed or no heat is evolved when the components are mixed. Right? The second says delta V is zero, that is volume of solution is nothing but sum total of the volume of two components. Correct? So mathematically say delta H mix is zero and delta V mix is zero for a ideal solution. Correct? So if they are ideal solution, they'll follow the Raoults law, that is P1 is nothing but P1 naught into X1. They'll follow this Raoults law. Now let's understand at molecular level why a solution is ideal and why a solution is non-ideal. Let's go deep into the molecules and try to understand why some solution is ideal and some solution is non-ideal. So let's take two components and let's name them A and B. So let's assume that this is component A and this is component B. So in the pure form, the intramolecular force of attraction between these components, for example, there will be force of attraction between these two A. There will be force of attraction between these two B. Right? Similarly here also there will be force of attraction. So there is a force of attraction between AA and BB. Correct? That is intermolecular force of attraction. Intermolecular force of interaction, I'll say. I'll not say attraction. It may be repulsion, maybe attraction. So now the moment you mix this in the mind mixture, there will be force of attraction between AB, or the force of interaction between AB. Also, there will be some force between AA and some force between BB also, right? There are three different forces. This is the pure form. Now in solution form, so we have AA, interaction between AB, PB and AB. Correct? Now, what is the trick? The trick is, this happens in the binary solution form. I am taking binary solution. Now, they told in this whole chapter is taking more binary solution, which has only one solid and one solvent. Now, if the force of attraction between AA and AB is equal to force of attraction between AB, that is this and this is equal to AB. I'm talking about the force of attraction. Then I have ideal solution. So in ideal solution, this force of attraction are all same, right? And this is a perfect solution. This is very rare. This is very rare. This ideal solution is rare. Is rare. We get near ideal solution. Near ideal solution we can get. So near ideal solution exists, and I'll show you some examples of that. Right? So examples of near ideal solution are N-hexane, N-heptane solution. So this is one. this N-hexane, this N-heptane. The other is bromoethane, chloroethane, and the next is this benzene, this is toluene. These are some of the examples of near ideal solution, right? So if you see these ideal solutions, near ideal solution, they look almost similar. See N-hexane and heptane, almost similar. Chloroethane, bromoethane, benzene, toluene, they are all similar. Thus, if you see the force of attraction between benzene and benzene, the force of attraction between toluene, and the force of attraction between benzene and toluene will almost be same. Same thing with this. Force of attraction between two chloroethane molecules or two bromoethane molecules, or force of attraction between bromoethane and chloroethane molecules will almost be same, right? Because they are almost similar molecules. Thus, you can see that these have near ideal solution. So let's understand the energies involved in making this solution to understand the whole process of ideal and non-ideal solution. Actually, there are 3 steps involved in making this solution. Step 1. The step 1 is solute. Assuming this is my solute and this is my solvent. Right? The first one is solute has to separate. Right? The first one is solute. This is separation. You have to separate the solute, and this is delta H is positive. This is heat is required. This is endothermic. The next is again solvent separation. See, to separate things you always need to give heat. Right? This is solvent again separation. Here also delta H will be positive and it has to be endothermic. The next one is solute-solvent cohesion, because once you break the bonds you have to find the bond, right? You have to form the bond here, correct? This is solute-solvent cohesion, and this is the trick part. Here it can be endothermic or exothermic. It can be either of these, right? It can be endo or it can be exothermic. That is, either heat may be required or heat may be emitted also. So we talk about delta H of the whole solution. You have to add all this delta H, sum of all 3 delta H, correct? Now the sum of all 3 delta H may be positive, may be negative, because this is positive, this is positive. If this is also positive, that is heat is required, the sum may be positive. If this is so much negative, for example, if it is 10, this is 10, this is 100, minus 100. So whole will be minus 80. This can be again positive or negative. And the sum actually tells whether a solution is feasible or not. Now, if delta H is positive, do you think whether you will be able to form a solution? Looking at this, you can see that delta H positive, you won't be able to form solution. But that is not correct, because to form solution we need, we need one more thing that is called delta G, and delta G is the Gibbs free energy. It is nothing but delta H minus T delta S. So if you see, even if this delta, I'll show you, even if this is positive, it is possible that delta G is negative. How? Because delta S is what is entropy change, and entropy change is always positive. Always positive. When you make a solution, delta S is always positive. Why? Because we are increasing the entropy of the system. We are increasing the disorderliness of the system, right? So this is always positive. Since this is positive, such a huge quantity, I am subtracting it. So delta G is always negative for a solution. If delta G is negative, you will be able to form a solution. Correct? So end of the day is delta G that matters. So in this case, when you add NaCl and water, delta G is negative, and thus you can easily form a solution. But if you're trying to form a solution between oil and water, you'll not be able to form the solution because of this factor. Okay. This is the just understanding of what are the energies involved when you form a solution, right? Solute separates, the energy is required. Solvent separates, energy required. Solute and solvent comes together. Sometimes energy is required, sometimes energy is given, and again the entropy of the system changes. So T delta is we have to take care. So the end of the day, what matters is delta G. If it is negative, then we'll be able to form the solution. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.